Good morning and good evening, everyone. And thank you for joining today's new product update webinar topic, enabling next generation automotive power distribution and electrification with TI high side switch controllers. My name is Surya Mishra, and I am a systems engineer at Texas Instruments. Before we get started, I would like to encourage everyone to ask questions throughout the presentation and using the Q&A box where we have Diego standing by to answer. And we will also be conducting a Q&A session at the end of the presentation. All right. So today we'll be talking about the introduction to the emerging zonal architecture and motivation towards 48 volt. We'll also deep dive into the typical power architectures seen for the battery management system and the zonal architecture, followed by the high side switch controller portfolio roadmap. So the image that you see on the left side mainly represents domain architecture wiring harness diagram. So this basically shows individual domain controllers where we have multiple loads being driven from individual controllers based on their function. For example, we can have the individual function controller for the lighting application, and all the lighting loads are being driven from this lighting domain controller. One of the shift or the emerging trend that we are seeing today here is that we are shifting from this traditional domain architecture towards the zonal architecture. In the zonal architecture, we have seen multiple zones which can be named as left zone, right zone, or rear zone, or maybe front zone also. So the major motivation behind moving from domain-based architecture to zonal architecture is basically to reduce the wiring harness or optimize the wiring harness in this vehicle network. And as more and more loads are getting added to our cars, and as we are moving towards software-defined vehicles, uh, the goal here is to optimize the power consumption, especially when the car is in parking state and it is only running on the battery. Another important trend that we are seeing here is that 48 volt rail is getting introduced to the input to drive some of the loads. Now the question here is why 48 volt? So the major advantage with 48 volt rail here is that for the same power dissipation, the current reduces by by a factor of 4. So the major advantage that we are seeing here is that that the for a OEM or a tier one, the wiring harness cost decreases because at 48 volt because the current levels are reduced now, and that's where uh, a smaller gauge wiring harness can be used for the 48 volt loads. Another trend that we have seen here is that generally in 48 volt system, a lot of these high current loads are being transferred to 48 volt first. And these loads can be like HVAC, power steering, or some loads. Uh, there are multiple OEMs or tier ones in regions like US, Japan, and China who have plans to move towards partial 48 volt or even up to full 48 volt, where we can have a whole car running on the 48 volt rail. So as a chip manufacturer, the challenge that we have here is that when we move towards 48 volt, our devices have to support the high voltage transient, which can go as high as 75 volt also. And apart from that, we also need to maintain a clearance between high voltage and low voltage pins, so that if there is any kind of humidity or any kind of leakage, we should not see any failure at a device level. So this is just a basic block diagram of mixed 12 and 48 volt architecture that we have seen across. So so this is the high voltage battery on the left side, or this could be alternator for the ICE vehicles. Then we have a DC-DC, which is basically converting from high voltage to 48 volt. Then from 48 volt, we have a power distribution unit, or it could be a front zone where all the 48 volt loads are there, and they are being driven by the 48 volt rail. Uh, we have seen a 48 volt lithium ion battery also for these kind of applications. Then from this 48 volt rail, the 12 volt rail is also derived using a DC-DC. And then uh, we have a common zone, or it could be a separate zone driving 12 and 48 volt loads as well. So the major point here is that as we are more closer to the battery, the currents can be very high. The load current can be very high, and it can range from 50 to even 500 amps. And uh, that's where there is a need for controllers which can drive external FETs, uh, uh, because after a certain level of current, it becomes really challenging to integrate the FET inside the same chip and achieve the same power density. So uh, uh, and one other important point to note here is that as we move away from the battery, the load current is going to reduce, and that's where we will have a much more integrated solution for the 12 volt as well as the 48 volt rail. And all these solution, especially on the controller side, my friend Diego will be presenting. So this is just a basic block diagram of the mixed architecture, and wherever we see the opportunities for controller. So all these are going to be high current loads or the disconnect switches in the BMS. So first of all, we have the BMS system where we can have a disconnect switch uh, driven by the high side switch controller, which is near the battery. Then we have the power distribution unit where the battery voltage and the DC-DC voltage from the 48 volt rail is getting odd, and both of them are driving, let's say, 12 volt rail, or some of them being driven from the 48 volt rail as well. In between, then similarly on the 48 volt side, we have the battery management system, and there is a disconnect switch for the 48 volt. Then in between, we have the DC-DC converter and the disconnect switches between the 12 volt and 48 volt rail. So for the BMS, so this basically shows a basic block diagram of a battery management system where we have the battery here, and this could be the battery management device. And these are the disconnect switches which are there in the system. So the key challenge here is that since this is very high current, so we may have multiple FETs in parallel. So we need to have a very high gate drive strength to drive these FETs. Apart from that, this controller also needs to have separate charge and discharge control in order to stop the current in either in forward overcurrent event or reverse overcurrent event. Another key point here is that since this controller is sitting close to the battery and this is going to be on always on, so the IQ of the controller itself has to be pretty low. and especially when the FETs are on. Uh, some other important features that are required here is that the controller needs to have reverse polarity protection as well. One other key challenge here is that that we already have this low side sense resistor near to the battery, which is basically sensing the current to determine the state of charge of the battery. So uh, the challenge here is that that if we can implement the overcurrent protection based on this low side current sense resistor, so that there is no need of extra current sense resistor on the high side, and this saves the BOM and space on the board. So the diagram on the left side basically shows a basic FET diagnosis architecture in the battery management system that we have identified. So the key challenge here is that how do we do the FET diagnosis when keeping all the FETs on or driving all the loads? So that's where we can have multiple paths in parallel. So the idea here is to do the FET diagnosis for, let's say, path one, while the path two, or let's say some other path is still driving the loads. So essentially, how it is done? Essentially, the middle node of this common source configuration of the MOSFETs can be sensed by the microcontroller, and the gate drive of these FETs can be individually controlled to check whether the FETs are stuck on or stuck off, and the FET diagnosis can be done in this way. So essentially, the ask here for a BMS system is to have a very low IQ controller with independent control of the charge and the discharge FET, and uh, configured in a common source topology, which also supports low side current sensing based over low side current sensing over current protection. Now coming to the power distribution box. So as we are directly replacing the melting fuse here, so the challenge here is that the device has to have an integrated I square T protection, which is programmable over, let's say, SPI interface, or it can be programmed using some passive components. Another point here is that some of the most of the motor loads have a very big capacitance at the ECU output. So devices needs to have some capacitive charging modes integrated into the device, which will help the which will help the controller to drive these loads. One other important challenge here is, since we are directly replacing the melting fuse, so I eventually, if we look at the IQ of a melting fuse itself is zero. So that's where we need to make sure that our devices are very low IQ, especially when the car is not running on the engine, it is running on the battery, and devices also needs to have this automatic load wake up feature, so that the MCU can also wake up from low power mode to active mode. One other feature that is required in these kind of devices here is the SPI interface, so that it helps it helps to reduce the number of IO pins in the system, and that these devices can be configured in a daisy chain configuration to sense all the important diagnostic parameters like output voltage, temperature, and the current information. Another key point here is that some of these devices have to be ASIL-B compliant. So these devices needs to be developed according to the ISO 26262 standard, having the limpom mode integrated, and some of the BIST or the self test integrated into the devices, so that it is easy for the OEMs or tier ones to achieve functional safety goals at the system level. Another key application for the high side switch controllers is the DC-DC circuit breaker, where we can have a circuit breaker on the 48 volt side and the other on the 12 volt side. So the the key challenge here is to have bidirectional current monitoring, so because the current can flow in either of the direction. And another key feature required here is the over voltage protection, because if anything fails on any of the side, right, we have to disconnect this switch in case of over voltage event, so that the fault doesn't propagate on the other side of the DC-DC. And again, since the currents are going to be very high for this kind of application, so we have to have a strong gate drive to drive the multiple effects. Over to Diego.
Thank you, Surya. My name is Diego. I'm the product marketing engineer for the high side switch controllers. And understanding the challenges in BMS, zonal architecture, DC to DC, power distribution units, the team created the high side switch controller portfolio with these 5 pillars in mind for the current products and future products. I'll quickly run through them. Strong gate drive, I mean, the first and most obvious feature. Integrated solutions that are in this type of architecture require strong gate drive to control parallel MOSFETs and to act as a circuit breaker. What this means is if it stays on, it stays on. If it's off, it stays off. In addition, when we parallel MOSFETs together to distribute power, we need all the MOSFETs to turn on at the same time and all the MOSFETs to turn off at the same time. So that's a very critical feature. Low power mode and low IQ. I mean, the nature of these loads is that the devices are very close to power supplies or power sources. And so low IQ is desired just so the device doesn't drain any energy from the battery or from wherever it's connected to. And then low power mode, as we start seeing more applications with power at all times, and the fact that these devices are so close to the power source, we need to kind of integrate a low power mode. So features like keyless entry, remote start, or safety alarms are always on, no matter if the car is off. And then the device slowly transitions to a fully on state when it's ready, when the car is ready to turn on. The other thing is with the end equipment mentioned, I2T is something pretty desirable, especially since we experience large transients above max operating current. In most cases, a mechanical fuse is present. So in order for the high side switch controllers to mimic the melting fuse, we kind of manipulate the current over time characteristics in a mechanical fuse to achieve the same result. So AKA like the I squared T. Not to mention this integrated programmable solution and simulation of a melting fuse is also self-resettable. So it can be stored away somewhere where the consumer doesn't have to be able to access the fuse box. On top of the I2T, the controllers, since they are so close to power sources, they need to provide fast short circuit protection and uni and bidirectional current monitoring, especially for DC to DC or power distribution units. Finally, as cars start becoming more autonomous and software defined, there's a lot of OEMs pushing the boundaries constantly in this aspect. The requirement for ASIL B becomes more and more prevalent, just because we need to be able to self-diagnose issues and internal to the switch. Fail-safes need to be integrated, because as autonomous vehicles, nobody's driving it, nobody's checking on it. So that's ISO standards require more and more diagnostics in ASIL B, and with more diagnostics come more pins for the MCU to control. So that goes hand in hand with SPI. SPI, we're able to reduce the number of pins an MCU needs by either daisy chaining or using multi-device serial communication, and reduce the number of pins while we're also providing the ASIL B. So on top of that, with SPI, we're able to do like real-time diagnostics on short circuit protection, I2T, under voltage, and all the other features that the controllers offer. And yeah, we can go on to the next slide. In the next slide here, this is kind of a glimpse of our current portfolio. The current portfolio, the main thing to mention here is that we have a 12-volt device, and we have a pin-to-pin compatible device in the 48-volt section. So whenever an OEM or a tier one is ready to move forward for a 48-volt architecture, they have to look no further than our 48-volt counterpart. And they're highlighted there in red. And then some other key features here to mention is the industry-leading low IQ. I mean, this is a constant requirement across switches. So yeah. And then the other thing is the current sense method. There's a lot of variation in how we can monitor current, just depending on whether the customer already has a current amplifier, or they want to monitor the FET VDS, or yeah. So there's a lot of flexibility there in current monitoring. And yeah, so this is a snapshot of our current portfolio. There's a lot of stuff in development with SPI and with ASIL B. So if you are interested more in those, please follow up with me, and then I can get you a more a better roadmap for what is to come. So leading to the roadmap, all of these devices that I showed that are on the screen now are releasing in December. So the 12-volt variants, along with the 48-volt variants, increasing our portfolio from 2 products to 12. So this is a big jump, and the team is working really hard to push these out. All of the samples are out right now for the controllers. We have EVMs as well, and yeah, and then we have some content planned. So I guess that leads me to the next slide, getting started. We have the overview of power switches, and then we have some reference designs out now. We have more reference designs coming and already in works with SPI and daisy chains happening. We also have technical content planned, and the ones that we already have out for certain, they were the most desired technical help. So reverse battery protection, powering capacitive loads, and temperature sensing. Those are out now on TI.com, and we're probably going to release a couple more by the end of next year. And then all the EVMs that we have released to date, and more coming. So that is what I had to present, and I want to leave it off for any questions. Give the last couple minutes for any questions. Well, I'll give it maybe a minute or two more. Well, if there's no more questions or no questions, I want to thank everyone for joining today, this new product update for the webinar. If you have any additional questions, please put them in the Q&A box, and we'll reach out to you directly. Please visit ti.com/NPU and for all upcoming NPU topics. And we look forward to seeing you again next week. Have a great day.